you wait for 1 or 2 more minutes.
Okay.
It always turns out that the people are very on time. So maybe 1 or 2 minutes and then we can start.
Oh, that's okay. So, right. Hello, everyone. As some of you can see, I'm not Sophie, but I'll be chairing the session for today. We're at the, if I remember correctly, second to last session of our Massive Stars lecture series. And today we'll have Priya Gojuldass, who will be talking about instabilities in hydrodynamic simulations of line-driven stellar winds. Priya is doing her PhD at the Embry-Riddle Aeronautical University in Florida. And she's for this session, she's has been supervised by Nicolas Muntz and Florian Driessen, both at KU Leuven. Right. Good. If nothing else, then Priya, I think you can begin.
Thank you for the introduction, Joel. So for my talk, I'm going to talk about the instabilities and hydrodynamic simulations of line-driven stellar winds. In the previous lectures, people have talked about smooth winds, but in massive stars, winds are unfortunately not smooth. So for this lecture, I'll be talking about the line-deshadowing instabilities and subsurface turbulence to explain the unstable behavior of the winds. As an overview, this talk is divided into two parts. The first part is about line-deshadowing instabilities. I'll be talking about what it is, its implications for observation, the mathematical framework of the LDI, its hydrodynamic simulation, and also touch upon the smooth source function. And the second part of this talk is about subsurface turbulence. I'll introduce what it is, then its observation, indication, and also its numerical modeling. Then I'll end the talk with the current challenges and future direction of this research. So before we get into the instabilities, let's see a small overview about line-driven winds. They occur in hot massive stars and are driven by radiation force on spectral lines. This force arises from momentum transfer when photons are absorbed by the ions, and it results in a very high mass loss and also has terminal velocity. And it's this mechanism is described by the CAK theory. On the figure on the right, it shows ions in the stellar atmosphere being accelerated outwards. They interact with the stellar photons and experience an outward radiative acceleration, which is the G-rad line that you see here, which acts against the inward gravitational acceleration, which is the G-grav line that you see here. So this imbalance in the force is what drives the stellar winds. David, in his previous talk, he spoke about the line-driven winds and its mass loss prescriptions. Please do listen to it if you haven't already. So let's get into the line-deshadowing instability. As we spoke in hot massive stars, the outward acceleration, it has strong radiation pressure. So the outward acceleration from this radiation pressure on the spectral line becomes very unstable due to Doppler shifts. This triggers the line-deshadowing instability, or LDI, and this amplifies any small perturbations in the wind. So this results in a two-component medium where it has a dense clumps that forms within a rarefied background. The figure on the right, if we go from, I guess if you go clockwise from the bottom left, we see that the clump likely begins near the surface of the star, and this overdense region, it grows and leading to spatial voracity, velocity gaps, and also shock fronts, which creates the X-rays. Further out, we can see that the turbulent motion, or clumping expansion, it continues to shape the wind. So as a takeaway from the slide, it's just LDI plays like a very crucial role in creating this structured outflow, and it directly impacts how we interpret mass laws and spectral features in observations. So as we established, line-driven winds, they're not steady, so they're inherently unstable due to the Doppler shifts. So even like a small velocity fluctuations, it can grow, leading to what is known as the line-deshadowing instability. So a small velocity bump in the wind causes like Doppler shift, which alters how ions absorb the radiation. So regions moving slightly faster absorb more photon and accelerate further, whereas regions, like slower regions, they fall behind. This causes the amplitude of the perturbation to like grow. The figure here shows velocity as a function of time, or sorry, radius. Velocity as a function of radius. So the smooth blue curve that you see here is the smooth wind solution that we get from the CAK theory. And this black wave is an initial small perturbation that occurs. Due to Doppler shift, the small perturbation experiences a velocity gradient. So we see like two regions on the small perturbation where the purple zone here, like on the purple zone here, the local velocity gradient enhances acceleration. So the local acceleration is like greater than 0. And in the green zone where the shadowing dominates, the flow over here sort of decelerates. So what happens is that photon of like a given wavelength can now interact with the multiple layers of gas at like different locations and amplify this instability. So the photon of like any given frequency or wavelength, it interacts once with the ion in the shadowing region, like this green shaded region, but it interacts multiple times on the deshadowing region on the purple zone. So due to this, what happens is like on the right, we see this small perturbation, it grows into like much larger structure. Eventually, this forms into like a clump or like shock that like characterizes and structures the stellar wind. So we saw what is line-driven instabilities. Now let us see the observation implications of the LDI. To understand how, to understand the massive star winds correctly, we need to account for clumping. So clumping strongly affects mass loss, and ignoring it can lead to like significant overestimates of this mass loss rate, which does distort like stellar evolution model and feedback predictions. A major issue in this is the degeneracy between the clumping and mass loss in the recombination lines like H alpha. Different combination of clumping factor and mass loss rate can produce like nearly identical line profile. So the figure here plotted for normalized flux versus the wavelength, it shows the absorption line, the H alpha profile in the black is the H alpha profile of the star. And we have different lines, different colored lines that are like the fits to this H alpha profile, synthetic fits. So the blue line and the red curve over here have like the same mass loss, but it has like different clumping factor, which demonstrates that clumping alone can alter the line shape. Meanwhile, the purple and green curve fits the data, and I guess it fits the data better, the H alpha line, but they assume like different mass laws, and which highlights this degeneracy issue. So to break this degeneracy and constrain like mass loss accurately, we do need to model this clumping more carefully. So in the previous slide, we saw about recombination lines, but in this slide, we're going to see about the resonance lines. To study wind structures in hot stars, we rely on the UV as well as the X-ray diagnostics. In the UV line, like the P Cygni lines, like carbon 4 or silicon 4, they are like especially sensitive to the wind structure, and it provides insight into the mass loss or terminal wind speed and clumping. The plot on the left shows the normalized flux as a function of the velocity. I guess it's scaled to the terminal wind speed. Here it shows a synthetic time series of the P signal profile. The time is like color coded. This variability reflects the influence of wind clumping, which affects how photons are absorbed over time. Because of clumping, if we want to do any quantitative science like constraining mass loss rate, it's like essential to combine optical and UV diagnostics to reduce the degeneracies we spoke about in the earlier slide. And there's also the X-ray emission, which adds like another piece to the puzzle. So shocks that are formed from the LDI, it heats up the wind material to like X-ray temperature, which like produces soft X-ray emission. And clumping variability makes this emission emission variable over time. This adds like a crucial constraint on the wind structure from the observational side. Now that we've seen the observational side, let's get into the mathematical framework of the LDI. So to describe stellar winds, we typically start with like three fundamental equations: continuity, momentum, and the energy equation. But for our purpose, we're going to assume isothermal gas and supersonic gas motion. And because we are doing perturbation analysis, we are like mainly interested in the momentum equation. So let's get into the momentum equation. This slide, it shows the momentum equation, which works just like the Newton's second law. So the upper or the equation at the top shows momentum equation for the smooth wind. On the left, we have acceleration, like how velocity changes in time and space. And on the right, we have forces acting on the gas, namely the pressure, gravity, and the radiation force. But we did establish in the previous slides that wind is unstable. So in the lower equation, it shows what happens when we perturb this wind. So we split the velocity into a steady state background and small disturbances. This lets us study how small changes evolve over time. And there is also perturbation in density, which comes from the continuity equation, but we did assume we're going to work with the supersonic gas motion. So the pressure forces here are much weaker than the radiation force. So this delta rho term, it becomes negligible, so we can ignore it. But what we are actually interested in here is the delta GR term, which is the perturbed radiation force, tracking how this perturbed radiation force respond to like a small velocity fluctuation will help us understand how instabilities grow and leads to the clumping formation in the line-driven winds. So delta zero is what we're going to find in the next slides. To solve the perturbed momentum equation, we express the velocity as a plane wave using Fourier modes. So here, delta V, the change in the velocity is like written as like a complex exponential, where V tilde is the complex valued amplitude, K is the wave number, and omega is the wave frequency. In an inhomogeneous medium, applying derivatives to this waveform like simplifies things. So the spatial derivative becomes like multiplication of ik, and the time derivative becomes multiplication of minus I omega. This reformalization reduces the partial differential equations into the algebraic ones that we'll see later. This makes the analysis more easier to see how perturbation grows or decays. To complete the linearized momentum equation, we now have to focus on the perturbed line radiation force. The total perturbed line force has like two components to it. One is the delta G direct, and the other is a delta diffuse component. The delta G direct is it's direct from the stellar radiation, while the delta G diffuse is from the scattered photons within the wind. So Joris, in his earlier talk, he explained how these two terms comes from the radiative transfer equation. But for our case here, we're going to ignore this delta G diffuse term since it's mostly symmetric and doesn't contribute much. So especially under the assumption that we're going to make a constant source function, it doesn't contribute much. So we are going to retain only the delta G direct, which is like key in driving the instability. The general expression here shows how the line force depends on the change in opacity and flux. Now, to analyze the perturbation, we assumed already we're going to use the plane wave solution for velocity, which converts time and spatial derivatives into algebraic factors involving the frequency and wave vector k. So applying that to the perturbed wind momentum equation will give us this equation at the bottom. This is an algebraic relation between the velocity and the radiation line force. So from here, our task is to compute this delta G line in terms of the delta V, which will allow us to like explore whether the perturbation will grow or like revealing the onset of the instabilities. And also, as I said before, we are working with the supersonic gas motion. So this A squared term becomes negligible, so we can ignore it. To understand how small velocity fluctuations affect the radiation force, we'll have to look at the perturbation to the line acceleration, focusing on the direct component, not the diffuse, but the direct component from the stellar radiation. In the first equation, we're expressing the total line force as a sum of the steady state term and a perturbed one, where the perturbation depends on change in opacity interacting with the steady, like the stellar flux. So here we assume that the perturbation remains optically thin. So the perturbed parcels experience like no changes in the radiation field. So that's why we dropped the delta F term we saw earlier. And the second equation over here is the perturbed line acceleration. We're not going to do all the math, but if we do solve the integrals, do all the math, and do perturbation through all terms of the line force, we get to this equation. And this result shows that the delta G direct is like proportional to the G thin as well as the delta V. The integral here, though, it depends on the line profile, but it does not change in time. So it's like represented by this constant. It doesn't really contribute much in our calculation as it's a constant. So this relation is like crucial as it lets us connect velocity perturbation directly to the radiative driving in our instability analysis. So this is the slide. We're going to get into our final steps of our linear analysis, deriving the dispersion relation. And here, again, we start with the line force. It splits into two component, direct and diffuse, just to recap. And as before, we focus only on the direct term, which drives the instability. Plugging this into the perturbed momentum equation in the Fourier space, where we consider the plane wave, and using our results, we are going to get this boxed expression as the dispersion relation. What the dispersion relation tells us is that how this perturbation behaves, whether they grow or decay, how they propagate, and how they interact with the medium. If the imaginary part of this omega is, if it's positive, then the perturbation grows over time, which signals the instability. And this is the nature of the line-deshadowing instability or line-driven instability, where small velocity disturbances are amplified by the radiation force. So Now that we have derived the dispersion relation in the previous slides, which connects the frequency and the wavelength of a wave, and it tells us whether disturbances will propagate or like whether it propagates or not. This has like a general solution, two possible general solutions, which depends on the Sobolev length. The first solution, if the Sobolev length is like very less than the unity, the perturbation is like longer than the Sobolev length. It doesn't really alter the local radiation force much. So we get like a smooth inward propagating Abbott wave with this first solution. While in the second solution, the Sobolev length is like greater than unity. In this case, the perturbation is like smaller than the Sobolev length. This perturbation, it modifies the hydrodynamic quantities within the Sobolev length and leads to the LDI. So this causes like an exponential growth in the time for like perturbed velocity. So the figure on the right, it shows velocity as a function of a distance from the star. On the left panel, we have an Abbott wave showing like a smooth localized velocity perturbation that remains like stable within the Sobolev length. On the right panel, we have the LDI, where small perturbation grows into like rapid oscillations in velocity over time. Again, it's measured relative to the Sobolev length. So what this plot illustrates is like how velocity varies with radius in both stable and unstable regime of like radiatively driven winds. So depending on the wavelength of the perturbation, the wind can either remain smooth or become unstable and structured. Like both happens in the wind. So to study how line-driven instabilities evolve beyond the linear regime, like we have to use the hydrodynamic simulations. Unlike the mathematical framework we did to get the dispersion relation, which uses only the linear limit, simulation can track like nonlinear growth of the perturbation, where like the clumping and the shocks like actually form. We model like wind dynamics under radiation pressure and follow how small disturbances break up the flow. Historically, this has been done using like 1D models, but there's been more recent work which explores the 2D models and magnetic field effects. So if we have the simulation, then we can compare the results of the simulations with the observations, such as the P-signal profiles or the X-rays we've discussed earlier, to test whether the predicted clumping matches what we see observationally. But before running simulations, we need to like find a way to account for how radiation interacts with the wind, specifically through a source function, which describes the spatial distribution of the emitted as well as the scattered radiation. Like now we need to include the diffuse radiation component while modeling. It's something that we ignored while doing the dispersion relation, like the numerical calculation. But solving like full radiative transfer with like scattering is like very, I guess it's like computationally expensive. So that's where the smooth source function comes in. What this smooth source function or SSF assumes is that the source function changes slowly over the Sobolev length, which allows us to simplify the problem we have. So instead of solving for like detailed scattering, we can model the radiation force using the line absorption alone. The equation at the bottom shows the SSF in like a optically thin limit. Here, I star is the intensity at the stellar surface, and mu star is the directional cosine. It's the it accounts for the angle between the stellar surface and the radiation direction. So in short, SSF offers like a practical way to include the radiation driving radiation driving in simulations. And it also like balances the physical realism we see observationally with the computational efficiency. So This slide over here shows the early stages of line-driven wind. So we have simulations. So on the left, we have like two panels. Here, the top panel shows the velocity, and the bottom panel shows the density as a function of the stellar radius, or sorry, as a function of radius. So here we see like a smooth wind profiles. The wind accelerates outward and the density like steadily decreases, matching what we would expect from like the classical 1D steady state model. But this is only the initial state, and line-driven winds are unstable. And so even small perturbation, they will eventually grow and it will eventually form like a clumps and shock. So on the right, this plot shows like a 2D cross-sectional view of the wind density distribution around the star. Over here, if we see at the early times, the outflow still looks uniform, but here the key difference is that in 1D, we can track how these initially spherical shell like breaks up as material travels farther. If like 1D were fully accurate, the symmetry, this initial symmetry that we see here would like persist throughout the structure. But as we see in the 2D simulations, these shell fragments like gives us like a more realistic picture of how wind evolved. So this sets the baseline for the onset of the nonlinear structure in the massive star wind. And this slide has like a snapshot of the simulation that we saw earlier. So again, the top panel over here shows wind velocity and the bottom panel shows the density as a function of the radial distance. We can see, we can like from this, we can like clearly see there's like two components structure forming here, like highlighted by these two circles. The purple circle over here marks the dense, slow-moving clumps, while the black circles marks the region of fast, low-density gas. So these features show like signatures of the LDI. So like a small velocity perturbation over here, it grows dense shells, like compresses and forms clumps. Meanwhile, the gas between these clumps, like they get accelerated and they get thinned out. So this sharp vertical jumps in the velocity and fall, like where it falls back is what results in shock, like that forms the shock. So the alternating pattern of this clump and the rarefied zone results in like a large density contrast, and also like it highly structures the wind. So LDI turns like an initially smooth outflow into like a turbulent and clumped medium. The main takeaway from this first part of the talk is that the LDI arises from like small velocity perturbation that alters the radiative line force, which leads to like feedback-driven growth. So the faster gas feels like stronger radiation pressure, which amplifies the instability. This also creates shocks and clumps, producing a highly structured wind. We saw this like analytically via the dispersion relation and numerically in the 1D simulation or the 2D simulation that we saw. So as a takeaway, LDI is like very crucial for understanding wind structure. It interprets the mass loss rates, it allows us to interpret the mass loss rate. And also it models the feedback of massive stars on their environment. So this concludes the first part of the talk. So the second part of the talk is about the subsurface turbulence. This research is like very recent compared to the line-deshadowing instability work. It's also, the turbulence here has like a more of a convection-like motion. So these are the 2 points that I want to stress in this slide before we get into the subsurface turbulence. Let's talk about the observational signature of the subsurface turbulence over here. So observationally, we see like macro turbulence broadening in O and B star spectra up to like 100 kilometers per second, which like cannot be really explained just by rotation or thermal motion alone. And similarly, there's like UV wind variability, like the discrete absorption component DAX or clumping, which suggests that they originate below the photosphere, likely due to subsurface turbulence or like gravity waves or rapid stellar rotation. But for our talk, we're going to concentrate on the subsurface turbulence. And this convection-driven velocity field also like it causes the Doppler broadening and and it shapes the absorption like the line profiles. So it gives like the broadened absorption lines. So on the plot on the right side, we see like a normalized flux plotted as a function of the velocity. Over here, these black dots they show the observed spectrum of the star, and the other lines, the red, green, and the purple line over here are the synthetic spectra that's like try to fit on this absorption line. Here, the red profile shows the correct rotation rate from like using it shows a correct rotation rate from the Fourier transform, but it lacks the micro turbulence component. So this results in like a narrow deep profile. The green curve, it like adjusts the rotation rate until it like best fit with the absorption line, but it still ignores the macro turbulence. So it doesn't like really get fitted well with the absorption line, the black dots that we see here. So and then there's this purple or blue line. It's very hard to see. It's like well fitted, but it does exist. There's this purple line that includes both the correct rotation and the macro turbulence, which matches the observed spectrum. So what this does highlight is that there is like need to include both the rotation as well as the micro turbulence while modeling line profile in massive stars. So, so what is subsurface turbulence? Hot massive stars in the main sequence, they have like a radiative envelope and a convective core. So, but however, these stars, they can like develop local convection zones just below the photosphere, which is like driven by peak in the opacity. These peaks occur when iron recombines, as shown in the Kuypen diagram on the right. So the figure here, it shows the evolution of the subsurface convection zone over time, where this green region indicates the convection zone forming near the surface of the star, particularly around the region of high opacity due to elements like iron or helium, actually iron and helium. At these depths, the radiative transport becomes like inefficient and convection becomes like the dominant mode of the energy transfer. So this convection doesn't extend throughout the envelope, but it triggers like localized turbulence beneath the surface. So, and massive stars also has like a high Eddington ratio, meaning the radiative force, they nearly balances out the gravity. This makes these outer layers to be like more susceptible to instabilities. So this subsurface turbulence is like thought to seed surface variability, macro turbulence, and also possibly even linked to the wind instabilities. Let's look at the mechanism of the subsurface turbulence. In subsurface layers, like the radiation can temporarily overpower gravity So the local Eddington factor becomes like greater than unity. As you can see on this image on the right, the gas cell over here, when the radiation can like overtake the gravity, this local Eddington, like the total local Eddington factor becomes greater than the unity, which allows this gas to move upward. But as it rises upward, it also like expands and it gets cooled. When this total Eddington factor, it becomes less than the unity. Because of this, it causes the gas to like fall back down because gravity takes over. This rise and fall process creates like an unstable feedback loop that triggers like convection-like motion. It's not like a classical convection, but it's enough to stir the layers and inject turbulence. And over time, this can lead to density inversion and even like artificial inflation in the envelope in 1D models, which is not physical, but it can happen. So to model this subsurface turbulence, we solve this full set of hydrodynamic equations. The continuity, momentum, energy, and the radiation equations. What these captures is the mass conservation, gravitational and the radiative forces, and the energy transport. This breaks the spherical symmetry and also leads to clumping, turbulence, and the observable wind variability. So this simulation over here, it illustrates like a high turbulence model where the subsurface plumes form and rise into the photosphere. Here, we can see like a dense structure that emerges on the left side, and it propagates upward with the velocity vectors. The velocity vectors are these black arrows that are overlaid. So these turbulent plumes interact with the line-driven winds above, seeding like variability and structure into the outflow. This connection between the internal convection or turbulence and the external wind explains how much of the observed clumping and changes in the spectral line profile. This shows like what happens below the surface, like strongly shapes what we observe. So the subsurface turbulence has been like analyzed using the perturbation theory, which predicts like two kinds of mode. One is the strange mode, and the other is the radiative convective mode. However, when we compare these predictions with like the results from the radiation hydrodynamic simulation, they don't align with what we actually observe. This discrepancy like tells us that linear theory is not simply enough, but nonlinear modeling does not work as well. So there is like a need for like a better linear theory. To wrap the second part of the lecture, so subsurface turbulence is very significant phenomenon in hot massive stars. It arises due to ion capacity-driven instabilities, which amplifies the local radiative acceleration. This process connects internal structure to the observable features like the spectral line profile, variability in mass loss rates, and it's like a future work, like looking ahead, like future work will involve coupling with magnetic fields, comparing synthetic spectra to the observations, refining 1D models like stellar wind prescription using the insights from the multidimensional simulations. As a general conclusion for this whole talk, observationally, we clearly see that the wind and stellar atmospheres are not smooth. They are structured and time variable. And we know at least two mechanisms that contribute to this, which are the LDI, line-Deshadowing instabilities, and surface instabilities. And we've also listed out some current challenges and future direction to these research. So LDI, it captures the small growth structure quite well, but it struggles to reproduce like large scale features like the discrete absorption components or DACs. But there's been some work that has been done on these papers. As future work to move forward, it needs like multi-dimensional effects, better characterization of the clump outflow, and also better treatment of the turbulent property, like studying the turbulent properties, and also more realistic radiative transfer and microphysics. For the subsurface instabilities, on the other hand, it's like less well understood. Their origin and how they interact with the radiation or magnetic field like remains an open question. It's also unclear how surface instabilities and LDI gets related. So some future work on surface instabilities like could include theoretical studies of the structure formation, 3D and MHD simulations of the wind base. Also, an effort to like unify this subsurface instability as well with the LDI to like get like a coherent framework. Thank you very much for listening to my talk.
Right. Thank you, Priya, for your very enlightening talk on line-deshadowing instability and surface instabilities. Good. Are there any questions from the audience? Please speak up and or raise your hand. Stan has a question. Please go ahead.
Well, thank you for this very quite impressive summary of two very difficult fields. For somebody coming from the outside and is still in graduate school, it's quite remarkable that you're able to kind of summarize two very challenging topics.
Thank you.
I think one of the key things to key outstanding questions is what is the relative role of these two different kinds of processes in understanding the structure that we infer from observations of, and you summarize this somewhat. But I think it's important here to kind of focus on a couple of different fundamental characteristics between the two different processes. The line-deshadowing instability is a compressive instability. It wants to compress things together, whereas the kind of structure that you're seeing from the subsurface is a kind of amplified gravity mode or some kind of overturning mode. It has vorticity, but not much compression. So in the context of trying to find explanations for highly compressive structures, the LDI is, I think, important. On the other hand, as you pointed out, the subsurface instabilities basically can have a much larger scale and therefore probably play a bigger role in wind variability and things like that, and things like the decks and stuff. But another point to be made here is that it's hard to put the two together, right? Because the subsurface treatments are basically based on an opacity model that basically is pseudo-continuum, whereas the line-deshadowing instability is inherently from line driving, and so for the latter, as you pointed out, you can't just use a simple local approximation for the driving. One of the things I think that you maybe didn't quite emphasize strong enough is that the instability, when you try to explain the instability, it's important to understand that the line-deshadowing instability only applies to very small scale perturbations. It's not a self-shadowing issue. It's just a coming out of and so. But anyway, the point I'm trying to say is that these two types of, I think both of them are needed to understand what we observe. Now, the final comment I would like to make is that if you just look at the issue of what happens in the acceleration of the wind itself, the subsurface structure plays a very important role because it generates a very large macro turbulence, very large turbulence, because when you have overturning motions, they're not limited to the sound speed. So the fact that you can see turbulent velocities of order 100 kilometers a second, Mach 5 or so, in terms of 5 times the sound speed, that completely changes the way the wind gets initiated. And if you just take the standard radiative driving using this SSF model or anything else, the prediction is that the wind would be very steeply accelerated from very low speeds to very high speeds, almost as like a step function. But when you put in this subsurface structure, you can understand a much smoother acceleration. Essentially, you put in a turbulence, a macro turbulence that competes with gravity rather than the sound speed, which is very small compared to the escape speed. Anyway, those are all important issues for the future studies here. And it's nice that you were able to summarize both processes. And I'm looking forward to seeing what comes about in the future. Thank you.
Thank you for the explanation.
Right. Any more questions from the audience? If not, I have one actually.
Yeah, no, wait.
Okay.
You have overlooked mine, sorry.
Oh, sorry.
Yeah. So, Priya, thanks a lot for this really very clever way of summarizing a lot of very difficult things, though also maintaining and explaining some of the mathematical and theoretical details. And of course, I agree with Stan about the problem of combining now these two different things. But before, I think since this talk will also be recorded and some other people will look, just let me point out that there might be also one slide which was not completely clear, and let me just clarify this. Namely, I'm speaking about what you call the smooth source function. So what you maybe did not mention here is that this source function term only plays a role if we consider the diffuse radiation field, which was neglected in all your previous talks. So without the diffuse radiation field, you would not understand why we need any kind of source function. So the source function is more or less, so it's not only absorption, but actually also line scattering. And so if we include this diffuse radiation field, then we will find some strange things, namely that part of the very strong instability due to the direct force, which you have carefully explained, is a bit damped, or in the lower part of the wind is strongly damped by this diffuse radiation field. So they counteract a bit. All these are details, but just to make sure that the source function, the smooth source function or the source function itself comes only into the play when we consider the diffuse radiation field and the diffuse force. So otherwise, I think this was a very clear talk, and I think I hope at least that a lot of people will have a look there and maybe understand now more than just from reading introductions. Thanks a lot.
Thank you.
Right. Not any more questions. Let me carefully double check this time. Stan has another question, I think.
Yeah, yes, as long as Joe brought it up, and indeed, since the talk will be recorded, it's important to understand that the smooth source function method was really quite a remarkably fortuitous. It was kind of it was, let me put it this way, it's a very bold approximation, which isn't clear that it should really apply, how well it should be apply. And it turns out to be very, very useful to understand this damping that Joe talked about. But there is another level of approximation called the escape integral source function. And the key point about this escape integral source function is that it comes into play a big role in the acceleration of the wind from the wind base, from going from the subsonic region to the supersonic region. And it is essentially a big part of why steady state models that you say co-moving frame and so forth have very, very steep acceleration. There's something called the source function dip that occurs around the sonic point. And so it's important to realize that this is just an initial approximation that was used to try to understand the damping that came from Leon-Lucy, the so-called Lucy line drag. But that actually there's a lot more subtle physics that one finds, especially in the region that transitions between the subsonic flow and the supersonic flow. And this is one of the reasons why I think it's so important to understand that that the subsurface instabilities that you talked about may actually make it moot that you don't have to actually use this simple one-dimensional model that accelerates very steeply, but rather you have all this macro turbulence that is generated by the subsurface structure. And then it actually allows you to get a very slow acceleration, a gradual acceleration of the wind in these multidimensional models. This is an area that I really think that future researchers should focus on. And I hope, I know all the people from the living group are looking into this. Anyway, so just to make clear that this is a very severe approximation, it turned out to be very useful to understand this damping effect, but that there's another, and then there's also, of course, these so-called co-moving frame treatments of radio transfer, but they have the difficulty that they always assume a monotonicity of the outflow, which is not obviously not true, because you have this very complex structure. And I know that Andreas Sander, who I think is on the talk here, has been worrying about this issue, and I think it's something that really should be looked at more in the future. Anyway, again, I think what you've done here is bring together two very challenging topics, which now I think future research can focus on how they get merged.
Thank you.
Right. Any further questions, comments, anything? Then I'll take my chair privileges and quickly ask one as well. So you talked about line-shadowing instabilities and these surface effects. You also showed us a kind of wave solution as well in the first part of your talk. Is there any way this is observable at all? That this grows big enough that we can see this? Or
From observational point of view,
Mhm.
I'm not exactly sure. Maybe I'll let the experienced person answer this question.
Mhm. Anyone with a good idea? If not, I'll do some digging myself. Good. Wait, Stan raised his hand. I see.
Yeah, I don't want to. I think the linear growth is something that's inherently hard to observationally confirm because it is small amplitude. But what happens near the surface, the way the instability goes, starts off, and in all the models that Priya showed, the model starts off smooth and then grows. But that's because of this cancellation between the drag effect that lowers the instability and the instability itself. But of course, now if we have a model in which the flow is already very turbulent at the surface, then that completely gets overwhelmed by the existing structure. I would comment that subsurface structure occurs only for stars that are close to the Eddington limit, that are close enough to the Eddington that the iron bump pushes you over. And so if you go to lower luminosity stars, they may be much more like the classical model where you go from a slow acceleration to a steep acceleration. And indeed, I think this may be one of the reasons for the so-called weak wind phenomena, that it's very hard to accelerate the wind if you don't already have an initial kick from the iron bump. So I think that's another area of great future study, important future study.
Thank you. Then if there's one else, I think we can conclude today's lecture series. So thank you, Priya, again for your great explanation on these both topics. I think next week we'll have the lecture on red supergiants. And there's another thing I need to mention. Oh, yeah, so this is the second to last lecture of our lecture series. I think after the lesson will be done, we will send another poll out asking for volunteers for our next lecture series as well for topics, both students and supervisors. All right, then if there's nothing else, if I'm not forgetting anything, I think we can conclude here. And
let's thank Priya again.
Thank you. Thank you for having me.
Okay, goodbye.